Hey everyone, so we are going to begin Unit 6. So this is Lesson 1. We're going to look at polynomial functions and rational functions in this unit. So moving to higher exponents aside from just an x squared. So remember that a polynomial is just an expression that has many terms with both constants and variables. Your leading coefficient refers to that number in the very front. When we talk about your leading term, that's the whole term in the front when it is in standard form. So from highest degree to lowest, your degree is your highest exponent. Coefficients, again, are the numbers with their signs, and then your constant is that last number in the back. So all of those vocab you should be kind of familiar with when I reference things. Okay, so some examples of polynomial graphs are shown here. They're always smooth curves or kind of straight lines, and they're usually continuous. And then your parent functions that you guys kind of graphed in the last one, or at least some of them, looking at linear, quadratic, cubic, quartic, quintic, and then so on and so forth. Notice that parent functions always pass through 0, 0. And we've already talked a little bit about transformations and what happens as we add numbers to certain parts of those equations and the shifts that begin. All right, so looking at what's called end behavior. And end behavior is exactly what it sounds like. We're looking at the ends of the graphs and determining what is happening. Where is it heading, or where is it coming from? Okay, so what happens on the left and right ends of the graph? Does it shoot way up, like toward infinity, or does it go toward negative infinity? And so we write that in symbols so we don't have to write it out in words every single time. I don't know why that's on there twice. Sorry about that. So just translating, again, that into symbols. So as I go to the right, we always start with our input, our x values. So you're just going to write as x approaches, and right is positive infinity. Or as I go to the left, and so as x approaches negative infinity. I tend to do negative before I do positive, but it doesn't really matter. You will always have a left statement and a right statement. The graph goes up, so remember your graph is notated as f of x. Up would be positive infinity. Or the graph goes down, so we have f of x, which is then approaching negative infinity. So these will vary, but you're always going to have a left statement and a right statement, and then one of these statements that goes with it. So we'll put that all together here with these functions here. So we have a cubic function and a quintic function. But just describing, you're going to essentially describe both arrows. So once again, you always have a left and a right. So you always have as x goes towards negative infinity, and as x goes towards positive infinity. And you don't have to put the plus sign, but just to give you an idea here. All right. Then it's just a matter is the graph going, so on the left, is it going up or down? All right, on the left it is going up, so f of x is approaching positive infinity. On the right, it is going down. Oops. So f of x is approaching negative infinity. All right, again, these f functions, or these f statements at the end, when it talks about your graph itself, the function itself, that's what will vary. Here we're still going to have as x goes to the left, so toward negative infinity, and as x goes to the right, so it goes toward positive infinity. You'll always have both of those. With this one on the left, our graph is going down, so it's approaching negative infinity. And this one, the graph is going down as well, so it's also approaching negative infinity. So sometimes those match, and that's fine. In fact, those match when the degree is even. And so that leads us right into kind of the formula for polynomials. So if your polynomial has an even degree and a positive lead coefficient, or if the polynomial has an even degree and a negative lead coefficient, or odd and even, odd and positive, excuse me, odd and negative. And looking at just kind of those two components will tell us what the end behavior will be. Okay, so once again, you're following the same formula every single time, but those different components tell us different things about how our graph is going to end. If it's even and positive, we're going to be going up and up. Think about a quadratic function, x squared. All right, so we're going positive and positive both ways. If it's even and negative, remember your transformations. This will flip over your x-axis. So it's going down and down. Think of a negative quadratic. So it's going to negative infinity and negative infinity. If it's odd and positive, think of like your cubic function. So like x cubed is odd and positive. Well, the parent function for x cubed looks like this. So we're going down on the left, but then up on the right. So we're going negative and then positive. All right. Odd and negative, that would be like negative x cubed. So that is flipped over the x-axis. So we're more like this. So we're going up and then down. So we're going to go toward positive infinity and then negative infinity. And so if you think of your parent functions there for just some of your basic polynomials, that will help kind of fill those in. Okay. And so that being said, you can look at something like this and rewrite it in just standard form. So negative 7x to the fourth plus 5x. So that you can observe here that we have a negative with a even exponent. And so without even graphing it, we're negative even, which is right here. So my end behavior for this is as x goes to negative infinity, your left statement, the function is going to approach also negative infinity because we're negative, negative here. And then as x goes to positive infinity, the function will still go toward negative infinity because it's even, so it always ends the same direction. Okay, so once again, you can use those formulas without graphing it then to identify what that's going to look like. Okay, so this one looks a little bit different, but think about, is the lead coefficient going to end up positive? And then what will the highest exponent be here? Okay, this one will be an odd degree because we have a 2 here, and then we have a 1 here. So we'll end up with a degree of 3 after we've multiplied this all out. So that's an odd degree. Our lead coefficient is going to be positive because we have positive times a positive. And so our lead coefficient will stay positive the whole way through. And so odd degree positive lead coefficient follows this formula here. So as negative, it goes negative. As positive, it goes positive. And one thing to kind of note here is anytime you have a positive lead coefficient, it will end on a positive note, is what I like to say for that. If it is positive, it will end positively. Okay, switching into zeros of a function and finding those solutions. We've done this before with just quadratics. So just running through that one more time. Remember that c is a 0 of your function p if you can solve for x equals c. Then that becomes a solution of the equation where that p of x is equal to 0. X minus c would be a factor of p of x, and c is an x-intercept of the graph itself. Okay, so c being a constant value that we can find. So if c is a 0 of a polynomial, you know all of these things. That if I tell you that 3 is a 0 then x equals 3 is a solution, which means that x minus 3 is a factor, and 3 is an x-intercept. And so with this one, we just factor, and we get x plus 4 and x minus 1. So those are the factors of our function, which means that x is equal to negative 4 and x is equal to 1. So negative 4 and 1 are the zeros, which also means they are the x-intercepts. Okay. What we haven't talked about yet is something called multiplicity, and I think I mentioned it like one time in class on the board maybe. And multiplicity is the number of times a zero occurs. So if you have x minus 3, this will just have a multiplicity of 1. Where if you have x minus 3 squared, that has then a multiplicity of 2 because that solution will occur 2 times. Okay. Now with multiplicities, that also tells you what a graph will do at that point. So if your real zero x-intercept with an even multiplicity, so it has a multiplicity of 2, for example, the graph will bounce or I guess a better word for this sentence is touch the x-axis, but not cross all the way through. So it'll just touch it. If it is odd, so if you have like a multiplicity of 1 or 3 or something like that, the graph will cross the x-axis. It will go all the way through it and continue going. Okay. So we can find the x-intercepts for these graphs and decide what will happen if we were to graph them. So for example, we have f of x is equal to x to the 4th minus 16. Go ahead and factor that. Okay, so factor down as difference of 2 squares. This one could even factor further, but we can just use our square root properties to solve this. If x squared minus 4 is equal to 0, then x equals 4, and x equals plus or minus 2. Sorry, x squared equals 4. Here, x squared plus 4 is 0, then x squared equals negative 4. These answers are non-real. And so we're not really going to look at this one. Okay, so your zeros are negative 2 and positive 2. Well, each of those just has a multiplicity of 1 because we only got each of those answers exactly one time. All right, so because of that, they will cross through the x-axis at those 2 points. Okay, so they cross through at both. So this one, go ahead and do the same thing. Let's factor that and then find the zeros. Okay, so I just factored by grouping here. So grouping the first 2 and then the last 2 and taking out their GCF and going down that way. Okay, so here we can see that you have x plus 1, which results in a 0 of x equals negative 1. All right, where here we have x minus 1, which results in the 0 of x equals 1, but this one has a multiplicity of 2, and it has a multiplicity of 2 because of this exponent right here on this factor. So if I solved both of these out, I would get the number 1 twice. All right, so at this 0, it just crosses through because it has a multiplicity of 1, which is odd. But at this 0, because of the multiplicity of 2, it's just going to touch the x-axis at that point and bounce off of it. Okay, so using that, you can do a rough sketch of the graph and describe its end behavior, the number of maximum extrema, so turning points. What its x-intercepts are, and if that has any multiplicity, what it does at those x-intercepts, the y-intercepts, and then you can give a sketch of the graph. And this is a really, really rough sketch. There's not even really a need to type it into your graphing calculator here. Okay, so going through 6, we have a odd positive in terms of end behavior. That means that as x approaches negative infinity, it's odd. And so it's going to start at negative infinity. Think of this is a cubic function, so think of your parent function here. And then as x approaches positive infinity, so will your function. And so because it is positive, it should end at positive. Because it's odd, it's going in the opposite direction as where it started. So these should not match if it's odd, ever. For part B, it wants max extrema. So how many possible extrema can you have? And as I stated before, this is turning points. Your turning points, we always look at the number of exponents. The degree here is 3, excuse me. So the number of max extrema is 2. It is always 1 less than highest degree. Part C, we have to factor to solve this. So I'm going to factor again by grouping. And so I take out an x squared and I get x plus 2. And then I take out a negative 1, I get x plus 2. So x squared minus 1, and then x plus 2. Solving this one, I get both negative 1 and positive 1. Solving this one, I get negative 2. All of these just have a multiplicity of 1, so they will all cross through. All right. My y-intercept here is negative 2, my constant at the end, so I'm going to write that as a point, 0, negative 2. And then I can sketch my graph. And like I said, this is just a really rough sketch. I still probably should have given you guys a little bit more room here of your graph. So I have a y-intercept of negative 2. I have x-intercepts of negative 1, positive 1, and negative 2. I also know how this starts and how it ends. So like, for example, I know that it needs to end going up this way, and I know that it needs to start by coming up this way. It should cross here, cross here, cross here, and cross there, because there's no bouncing. It just crosses at all of them. And then that's kind of a rough sketch. So if you type that in your graphing calculator, the general shape should look the same. Okay? So go ahead and kind of run through and try this second one on your own. Okay, so for this one, for the degree, add up all your exponents. We have 3 plus 2 plus 1 is 5, 6, so it is even. And then negative. And so even, negative, it starts down, and then we'll end down because even ones always end the same direction. So we have negative, negative, positive, negative. Same thing with your max number of extrema. We're going to have 5 possible turning points because that is 1 less than the degree when we add up our degrees. So to find my zeros, I just set each of these factors, it's already in factored form for us, equal to 0 and solve. So negative 2x cubed equals 0 means that x is 0. But I have a multiple of 3 because of the 3 exponent. Negative 1 would equal 0, multiplicity of 2, and then positive 2 will equal 0 with a multiplicity of 1. Odd multiplicities will cross, even multiplicities will touch. My y-intercept, if I plug in a 0, the whole thing goes to 0. So 0, 0. Then you can just kind of sketch, knowing the points that you know and the end behavior. It doesn't have to be identical to what you would see in a graphing calculator. So I know that it crosses at 0, 0. That is both an x-intercept and a y-intercept. I know that it crosses at negative, or bounces off negative 1. And I know that it goes through 2. Okay. I know that it starts from the bottom. Again, it's going to just touch this one, but bounce off of it, come back down. It has to cross through here, and then it has to cross through again right here. And so again, rough sketch. You can see I have 1, 2, 3 turning points. This is a max number of extrema, not a certain number. And so I can have up to 5. But it doesn't have to equal 5 as long as I don't go over it. Okay? And so that's it. Let me know if you have any questions, and have a great night.